And what is the total number? The total number will be if I multiply all the choices. Like n choices first, then n minus 1, and then this. So 5 plus 4, 5 into 4 into 3 into 2 into 1. So these many choices, the number of ways that I can do this thing, I will be able to calculate the total number of ways. Now if I look at this configuration, then I see that there are pairs like 1, 2, then 2, 1. Similarly, 1, 3 and 3, 1. 1, 4 and 4, 1. So we are having pairs here like 1, 2 and 2, 1, 3, 1 and 1, 3 are 1, 3 and 3, 1, and similarly the 1, 4 and 4, 1. So these pair, each of the pair is representing one state, and it means that we will have to divide the total number of choices by the picking number, which we call like n1, and the factorial of that. So to convince ourselves that we are right, as here we were picking two particles, so here n1 was 2. And n1 factorial will be 2 into 1 is equal to 2. So we will have to divide this by n1 factorial, and to convince ourselves that we are doing the right thing, let me consider the n1 is equal to 3. Like we are picking 3 particles now. And what will be the number of ways now? So if I just want to pick n1 equal to 3 particles, then the same configuration can be built in n1 factorial ways. Like start from 3 particles, I can pick 1, 2, 3, then 1, 3, 2. Similarly, 2, 1, 3 and 2, 3, 1, and 3, 1, 2 and 3, 2, 1. Means with 1 I pick 2, 3. Then with 1 I can pick 3, 2. With 2 I can pick 1, 3, and with 2 I can pick 3, 1. Then with 3, 1, 2, and with 3, 2, 1. So these are the number of ways. How many ways? These are 6 ways. So 3 factorial is equal to 3 into 2 into 1, and number of ways is actually 6 here. So I can write that in order to exclude the pairs or exclude the identical cases, means the pairs that were coming in there is identical, we will have to divide the total number of configurations which are n into this by n factorial. So this implies that n into n minus 1 into n minus 2 and n minus n1 plus 1, we will have to divide this whole by n1 factorial. And this is equal to, I can write this one is n factorial, because n minus 1, n minus 2, and it is decreasing. And finally we will reach 1 here. So this I can write is n factorial divided by n1 from here, n1 factorial, and then n minus n1 whole factorial. Now the question is that can I write this relation in this form? So I will have to prove this, that yes, this can be written in this way. So let's prove this one, that we can write this result in this form. Just work it out. And we can work it out like this. That n factorial I can write is, this is equal to 1 over n1 factorial, and this n factorial I can write n into n minus 1 into n minus 2 and so on up to n minus n1 plus 1, and then I will write this thing. I will write n minus n1 plus 1, and then further it will be n minus n1 and n minus n1 minus 1, because this number will be decreasing, n minus n1 and minus 1. Okay, let me write it here, minus 1, and this will reach up to 1. Divide by, this whole divided by this one, n minus n1 whole factorial I can write is n minus n1 into n minus n1 minus 1 and so on, and it will reach 1. So this one is cancelling with this. This whole means this is going to 1 and this whole is going to 1. So the numerator, this portion will cancel with it, and we will again get this thing n into n minus 1 into n minus 2, and this will go up to n minus n1 plus 1, and this whole is divided by 1 over n1 factorial. This is the total number of ways divided by the identical, means excluding the identical pairs. So the identical pairs will always be depending on the number of choices we are picking the particles. We remember that each particle is having d1 choices of states to have energy E1. Like when the energy is E1, the degeneracy is D1. So we now consider an example, and in that example we consider that D1 is equal to 2. That is, that the two states will have the same energy, and N1 is equal to 3. That we have 3 particles, and those 3 particles will occupy 3 spaces such that 2 of the states will be the same. And like 2 means we will have like psi 1 and psi 2. These are the states which are having the same energy E1, and 3 particles will have to occupy these 3 spaces. So I can put all the 3 particles in psi 1 or in state 1, or I can put one particle in 1 and another particle in 2. Similarly, psi 1, psi 2, psi 1 or psi 1, psi 2, psi 2. Or I can put in psi 2, then psi 1, psi 1, and psi 2, psi 1, psi 2, psi 2, psi 2, psi 1, and psi 2, psi 2, psi 1. Okay, understand this one again. I'm having 3 particles. So I will put the 3 particles in 3 spaces. And as the degeneracy, the energy of the state is E1, and it is having a degeneracy D1. And D1 I consider is 2. That there are 2 states that have the same energy. So now I will have to put 3 particles. I can put one particle in psi 1, another particle in psi 1, and another particle in psi 1. That is one possible way that I can do. Or I can put all the 3 particles in psi 2. Here this one is psi 2. Either I can put all the 3 particles in psi 1, or I can put all the 3 particles in psi 2 spaces or states. Now I can do this one as well, that I put the 2 particles in psi 1 and 1 particle in psi 2, or psi 1 and psi 2 and psi 1, and so on. So, how many different ways that I can put them? Now I can calculate the number of ways, 4 here and 4 here. So the total number of ways is actually equal to 8. And this I can write 2 to the power 3. So here 2 is the degeneracy, and this is the number of particles that I am putting. So generally I can write this thing, that this is d1 to the power n1, and this is equal to 8. So if I will have each particle 1, 2, 3 and has the choice of psi 1 or psi 2, so number of combinations will be 8, and generally I can write that with dn degeneracies and nn, the number of particles that I am placing will be the number of choices. So dn to the power nn will be the number of choices. Here the number of choices comes out to be 8. And this way I can write my final expression, and the expression is this one. So when I will include the degeneracy, this number of choices will multiply with this one. The number of choices increase, and now the total number of choices will be n factorial. So the total number of choices are then n factorial divided by n1 factorial n minus n1 whole factorial, and this will come along with it, which will be, as I'm writing n1 here, so this will be d1 to the power n1 here. And similarly, if I write from here, if I write for the next picking, like here I have picked in 1 particles, and these are the number of choices. Now when I will put in 2 particles, means when I will pick in 2 particles, what will be the number of choices? And similarly in 3 particles, and the total number of choices. Now if we put this all together, then n factorial d1 to the power n divided by n1 factorial n minus n1 whole factorial. So this is telling us that if we pick n1 particles from n particles such that each n1 particle can be in different d1 states. Now the next step is that we want to pick in 2 particles. So in how many ways we can do this thing? What will happen? That n will now come to n minus n1. These are the remaining choices. N1 will go to N2 as we are picking in 2 particles, and D1 will go to D2 as the degeneracies will be different, and this expression will go to, for n I can write n minus n1 factorial, and then d2 to the power n2 divided by n2 factorial and n minus n1. So for n I will write n minus n1, n minus n1 minus n1, so it will become minus n2 and this. Similarly, when we will do for a 3 particles pick, like when I pick in 3 particles, so what will happen? N minus n1 will go to n minus n1 minus n2, and n2 will go to n3, d2 will go to d3, and this implies that the relation will become n minus n1 will be replaced by minus n2 factorial d3 to the power n3 divided by n3 factorial and n minus n1 minus n2 minus n3 whole factorial. And this will continue. Like we go for n4 particles and so on. So finally, in order to find the total number of ways, q n1, n2, n3, this will be equal. We will have to multiply this and with this, and it will be equal to the very first one, which is n d1 n1 over n1 factorial n minus n1 factorial. This is multiplied with this n minus n1 factorial d2 n2 divided by n2 and n minus n1 minus n2 multiplied by the last one, which is n minus n1 minus n2 d3 over power n3 divided by n3 factorial and n minus n1 minus n2 minus n3 factorial and multiplied by another and so on. Now here I can see that this is cancelling with this and this is cancelling with this. So what we get, similarly this will cancel with the other and so on. So finally I will get that this thing is equal to n factorial, this will survive, while d1 n1 then d2 n multiplied by d2 n2 multiplied by d3 n3 and multiplied by d4 n4, and here n1 factorial multiplied by 2 factorial and 3 factorial. So the multiplication I write with the product pi, and n runs from 1 up to infinity, dn to the power n divided by n factorial.